In the second part of the video, we're going to go over the chi-square tests. From last week, with the t-test, your dependent variable, remember, had to be at the interval level measure. And the independent variable had to be nominal with exactly 2 categories. The analysis of variance, you ran that test when your dependent variable was measured at the interval level. Your independent variable happened to be at the nominal level, but with more than 2 categories. Chi-square changes this up. Your dependent variable for a chi-square will be measured at the nominal level. So, for example, if your dependent variable was some sort of yes, no. Did you vote or not? Yes or no? It's nominal level. The independent variable also measured at the nominal level. And for both the dependent and independent variables, the number of categories does not matter. So for a dependent variable, whether or not you voted, you could have yes, no, refuse to answer, or don't know. Still nominal level variable, 4 different categories. For your independent variable, maybe you wanted to, again, look at party identification, and you had Democrat, Republicans, Libertarians, and Green. You have 4 categories for the dependent variable, 4 categories for the independent variable. You can certainly run a chi-square doing this. More often than not, however, your dependent variable will probably have just 2 categories and your independent variable 2 or 3. So this is a rudimentary test on the relationship between 2 nominal variables. 1 independent variable measured at the nominal level and 1 dependent variable measured at the nominal level. So for example, section 1.1 of the notes shows a contingency table where it looks at the effect of race, with the categories being black and white, on participation. High participation versus low participation, whatever, however you want to measure participation, voting, signing petitions, attending council meetings, etc. So we'll consider high participation. They attend a lot of city council meetings. Low participation, they don't attend many city county meetings. In the rows is where your dependent variable will be listed. So you can see participation in this case is the dependent variable, and it's high and low. The independent variables are arrayed in the columns. This would be race, and it's 2 categories, black and white. So with 2 categories in each variable, we have a 2 by 2 table, meaning there's 2 substantive rows and 2 substantive columns. The 2 substantive rows are the high participation and low participation, and the 2 substantive columns are black and white. So if you look at the table, it's not a 3 by 3. Don't count the totals as separate rows or columns. Look at the substantive, what the variable categories are, and you see there's 2 categories for both the dependent and the independent variable. In the table, as I reproduce it here, they give you they have the race in the columns, black and white. In the rows, they have participation, high participation, and low participation. And they put the totals for you in the row totals and the column totals. So we got a 2x2 table. The way in which to read this is there out of 100 people surveyed, that's your total down at the bottom right, that's your N, the number of individuals in the survey. 35 black individuals indicated that they were high participants in city county, in attending city council meetings. 15 blacks were low participants in city county meetings. That column total is 50, so a total of 50 blacks were surveyed. Whites, we have 30 high participating whites, 20 low participating whites in city council meetings, and we've sampled a total of 50 whites. If you look to the row totals, we have a total of 15 plus 20, or 35 low participants, and 35 plus 30 high participants, 65. And so that's the table reproduced from your notes. What does the chi-square do? It will determine if there is a statistically significant relationship between your independent variable, race, and your dependent variable, participation. Like the t-test, like ANOVA, it will not establish causality. You will have to go to do regression to establish that. This will, however, indicate if there's a statistically significant relationship between the two variables, so that you could then go and try to examine the causal relationship with a regression analysis, which we'll do in a couple weeks. The null hypothesis of a chi-square test is that there is no relationship between the two variables, between race and participation, or your independent variable and your dependent variable. So the null hypothesis is that of independence between the two variables. You could formulate a research hypothesis. Maybe before collecting the data, you say that race does have an effect on participation. You might hypothesize that whites participate more. In this case, it was city council meetings and city council meetings compared to blacks. So the research hypothesis says that the two variables are dependent. The dependent variable participation depends on the independent variable race. A null hypothesis of no effect says that they're totally independent of each other. They don't affect each other. To calculate a chi-square test to determine if race and participation are statistically significantly related to each other, you will ultimately run the equation in your notes. Chi-squared equals the summation, and the summation is all on the outside, so you do the summation last. In the denominator, or in the numerator, you take the observed values minus the expected values, square it over the expected. And this sigma or summations on the outside, it does do that process at the very end. If you look on the first page, the new notation, FO means observed frequencies. These are the numbers that you see in the table of data you collected. So this 35, this 30, this 15, this 20 are all observed values. So 35 is an FO, 30 is an FO, 15 is an FO, 20 is an FO. So we have those. FE is the expected frequencies. And FE, or the expected frequencies, is what we should see in these tables, in this table, if race and participation are independent. If there is no relationship between race and participation, what numbers should we see in these substantive cells? It doesn't necessarily mean an even split. It certainly depends upon the number of people you survey of each race and the high and low participants that are in there. So it's not going to be a perfect 50% in each cell in every case. Sometimes it will be, sometimes it won't. But ultimately we're trying to say that we've observed these values. 35 high participating blacks, 15 low participating blacks, 30 high participating whites, and 20 low participating whites. If race and participation are not related to each other, what numbers should we see in these four cells? What should we expect to see? To calculate the expected values, you take your row marginal, you multiply it by a column marginal, and then you divide by n, or the total number of observations in your survey or in your table. What are the marginals? They are what appear in the totals column or row. So this 65 is a row marginal for high participation. This 35 is a row marginal for low participation. The column marginals are the totals for the columns of the substantive categories. So 50 is a column marginal for black, and this 50 is a column marginal for white. And N is the bottom right hand corner, the total number of observations or people surveyed, and that's 100. We use this formula, FE equals a row marginal times a column marginal over N, to figure out the expected values we should see in each of these substantive cells. So we observed 35 high participating blacks. If there's no relationship between race and participation, what should we see in that cell? Same thing for high participating whites. We observed 30, but if there's no relationship between race and participation, what number should we see in that cell? And so on for the 15 and the 20. The way to figure out what we should see in each cell is to use this equation for each substantive cell in our table. So if you go clockwise, we will start with high participating blacks. What should we see if there's no relationship between race and participation? We observe 35. What should we see if there's no relationship? So you do FE equals the row marginal for this cell is 65. Multiply it by the column marginal for this cell, which is 50. And then divide by N of 100. $65 times 50 is 3,250. Divide that by 100. you get 32.5. So that's the expected value that we should see in this cell in the black high participation. We observe 35. If there's no relationship between race and participation, we should see 32.5. I'll put that in black. Going clockwise, starting from the upper left. Now let's go to the northeast cell, high participating white. Using the FE equation, the row marginal for high participating whites is 65. Multiply that by its column marginal, which is still 50, just the other 50, and then divide by n of 100. And you should get the same answer. 65 times 50 is 3,250, and divide that by 100, it's 32.5. So if race and participation are independent, there's no relationship, then we should expect to see 32.5 in the high participating white cell. Now go to the southeast into a low participating white cell. What should we see in this box where we observe 20? You take the row marginal of 35, multiply it by its column marginal of 50, and divide by n of 100. That's 1750 over 100. Should be 17.5. So we should see 17.5 in this column, or in this cell, excuse me. Now for the last one, low participating black, do the FE equation. We observed 15, the row marginal is 35, column marginal is 50, divided by an n of 100, and you just happen to get the same answer, 17.5. So if there was no relationship between race and participation, we would expect to see 32.5 in the high participating cells, so and split equally between black and white, and for low participation, we should see it split evenly between black and white at 17.5. Won't always be that clean. It depends upon your marginal numbers. Once you've done that, you can now calculate your chi-square statistic given on the notes, where you take the observed value for each cell, subtract out the expected value, square it, and then divide it by the expected value. Do that for each substantive cell in your table. So we'll be doing it for 4 of these. So 35, 30, 15, and 20. Those are the observed. We'll be comparing those to their expecteds. And then we'll add up the values at the end. So again, going clockwise, starting at the northwest with high participating black, we observed 35. We expected 32.5. We're going to square that difference and divide by our expected of 32.5. So you will get 35 minus 32.5. 2.5 squared over 32.5. You get a 0.19. Okay, go clockwise. Now we're going to the cell where we observed 30 high participating whites. So we observed 30. We expected 32.5 in that cell. You're going to square that difference and then divide by the expected 32.5. This happens to be negative 2.5 squared over 32.5. And when you multiply that out, you should get the same thing as before. Negative 2.5 squared is 6.25, and then divided that by 32.5, you get a 0.19. Continue going clockwise. Now to this cell of low participating whites, we observe 20. We expected 17.5. Square that difference and divide by the expected of 17.5. You get another 2.5 squared over 17.5. So 6.25 divided by 17.5. You get about 0.36. Now go over to the southwest cell, low participating black. We observed 15, expected 17.5. Square it and divide by the expected of 17.5. You get a negative 2.5 squared over 17.5, and you get 0.36. So now that you've done that for each of the substantive cells, the last step is to add them all up. So 0.19 plus 0.19 plus 0.36 plus 0.36. And the sum is 1.1. That is your chi-square value as 1.1. Now, what does this mean? Is this statistically significant? Well, you have to go to a chi-square table, a special distribution, and figure out your degrees of freedom. The degrees of freedom formula for a chi-square is r minus 1, which is the number of substantive rows you have, minus 1, multiplied the number of columns, minus 1, those being the substantive columns. So we have 2 substantive rows, the high and the low participation, and 2 substantive columns, black and white. So 2 minus 1 times 2 minus 1, your degrees of freedom end up being 1 times 1, or 1. In the chi-square table in the book, on page 529 in the blue book, the column that you want to pay attention to is going to be the 0.05 column. That's your 95% confidence column. The 99% confidence is the 0.01 column. Okay, so in this case, we're looking at 0.05. You see the degrees of freedom off to the right. In a column, we have 1 degree of freedom. So the chi-square critical value for statistical significance is 3.84. So you can think of the table as your chi-square critical with 1 degree of freedom in the 95% column. Your critical value is 3.84. So anything above a 3.84 or 3.84 itself will be 95% significant. The chi-square that we calculated, or the chi-square we obtained, happened to be just 1.1. So it does not meet and or exceed that threshold of 3.84. And so we cannot conclude at the 95% confidence level, or we cannot conclude with 95% confidence that race and participation are related. We have to accept the null hypothesis of independence between the 2 variables. Again, we cannot discuss causality quite yet. We need to do that with regression. Right now, we're just saying that the 2 variables are not correlated in a statistically significant manner. And that's because the chi-square value of 1.1 does not exceed the critical value of 3.84. But again, the big limitation is we don't have a causal direction, and we don't know necessarily which variables or which categories are pushing the relationship if it were statistically significant. In the next video, we'll see an example like the homework, where the relationship is statistically significant. You can see what happens and how we go about interpreting that. But from here, you can stop, say there's no statistically significant relationship. Race and participation are independent.